Hello there, and welcome to my channel. I'm so glad you've found your way here tonight. Whether you're settling in after a long day, your mind is buzzing with thoughts that won't quiet down, or you simply love drifting off to the gentle hum of cosmic mysteries, this video was made just for you. Tonight, we're going to take a peaceful journey through one of the universe's most elegant secrets, gravitational waves, the invisible ripples that flow through the very fabric of space and time. But before we begin this dreamy exploration, I'd love to know, where in the world are you listening from right now, and what time is it where you are? Are you tucked away somewhere cozy, perhaps watching the stars through your window, or maybe you're in a bustling city where the lights never quite fade? There's something beautifully poetic about the fact that no matter where you are, these same gravitational waves are washing over you right now, carrying stories from the deepest corners of the cosmos. If you find these gentle scientific wanderings soothing or intriguing, I'd be ever so grateful if you gave this video a like and perhaps subscribed. It helps other curious souls discover this quiet corner of wonder, and it means I can keep crafting these soft cosmic lullabies for you. Now, I do hope this isn't too fascinating that it accidentally keeps you awake, but if it does, at least you'll drift off knowing something beautiful about how the universe whispers its secrets to us. So settle in, let your breathing slow, and let's embark on this tranquil voyage into the rippling depths of space-time itself. Picture this. You're sitting by a perfectly still pond on a calm evening. The water is like glass, reflecting the twilight sky in perfect mirror stillness. Now, imagine dropping a single pebble into that serene surface. What happens? Ripples spread outward in perfect circles, carrying the energy of that tiny disturbance across the entire pond. The water itself doesn't travel anywhere, mind you. Each drop simply bobs up and down as the wave passes through, but the energy, the information of that splash, travels gracefully from the center to the shore. Now, hold that image in your mind as I tell you something rather extraordinary. Space itself behaves much the same way. When something dramatic happens in the universe, when massive objects accelerate and dance through the cosmos, they create ripples not in water, but in the very fabric of reality. These are gravitational waves, and they've been washing over us, through us, and around us every moment of our lives, carrying whispers from some of the most violent and beautiful events the universe has ever known. But here's what makes this story so wonderfully soothing. These waves are unimaginably gentle by the time they reach us. A gravitational wave from a collision between two black holes billions of light years away might stretch and compress space by less than 1/10,000th the width of a proton. That's smaller than anything you could ever imagine, tinier than the smallest thing you've ever worried about. And yet, somehow, we've learned to listen to these cosmic whispers, to detect these ethereal messages from the deepest reaches of space and time. To understand how we got here, how humanity learned to hear the universe's quietest songs, we need to travel back through time, to meet a man whose wild hair and gentle eyes hid one of the most revolutionary minds in history. Albert Einstein, working in his study over a century ago, was playing with equations that would forever change how we see reality. In 1915, he gave us his theory of general relativity, a breathtakingly beautiful description of gravity, not as a force pulling objects together, but as the curvature of space and time itself. Imagine space-time as a soft, stretchy fabric, like a rubber sheet pulled taut. Place a bowling ball in the center, and it creates a dip, a curve in the fabric. Now roll a marble nearby, and it will spiral around that depression, following the curved path created by the heavier object. This isn't some mystical force reaching out and grabbing the marble. The marble is simply following the straightest possible path through curved space-time. That's gravity, according to Einstein. Mass and energy tell space-time how to curve, and curved space-time tells objects how to move. But Einstein's equations revealed something even more profound. If you were to shake that bowling ball back and forth, the ripples in the fabric wouldn't just affect things nearby. Waves would spread outward at the speed of light, carrying information about that disturbance across the entire sheet. Similarly, when massive objects in space accelerate, particularly when they orbit each other in tight, spiraling dances, they create ripples in spacetime itself. Einstein himself wasn't entirely sure these gravitational waves were real. The mathematics suggested they should exist, but they would be so incredibly weak, so impossibly faint, that he doubted they could ever be detected. He once wrote to a friend, "It is doubtful whether such waves exist at all." Even the great Einstein sometimes underestimated the ingenuity of future scientists and the exquisite sensitivity of the instruments they would build. For decades, gravitational waves remained purely theoretical, mathematical ghosts haunting the equations of general relativity. But the universe, as it so often does, provided hints that these waves were more than just mathematical curiosities. In the 1972nd, two astronomers named Joseph Taylor and Russell Hulse discovered something remarkable: a pulsar, a rapidly spinning neutron star that acts like a cosmic lighthouse, sending out beams of radiation as it spins. But this wasn't just any pulsar. It was locked in orbit with another neutron star, and the two were spiraling closer and closer together. By timing the pulses with extraordinary precision, Taylor and Hulse could measure the orbit of this cosmic dance with incredible accuracy. And what they found was exactly what Einstein's equations predicted. The orbit was decaying at precisely the rate it should if the system were losing energy by radiating gravitational waves. It was like watching the ripples spread from that cosmic pond, even though they couldn't directly see the waves themselves. For this discovery, they were awarded the Nobel Prize in Physics, and humanity had its first indirect proof that gravitational waves were real. But seeing the ripples spread across a pond is very different from feeling the gentle touch of those waves as they pass by. To directly detect gravitational waves, scientists needed to build instruments of almost unimaginable sensitivity. They needed to measure changes in distance smaller than a fraction of the size of a proton, changes so tiny that they make a grain of sand look like a mountain by comparison. The solution was both elegant and audacious: laser interferometry. Picture two long tunnels stretching for miles in perfect straight lines, meeting at a right angle like a giant letter L. At each end of these tunnels sits a mirror, suspended by the most delicate systems engineers could devise, isolated from every possible vibration, from passing trucks, distant earthquakes, even the thermal motion of atoms in the mirror itself. A laser beam is split and sent down both arms simultaneously, bouncing back and forth between the mirrors hundreds of times before returning to where it started. Under normal circumstances, these two laser beams travel exactly the same distance and arrive back at the same time, creating a specific pattern of light and shadow. But when a gravitational wave passes through, it does something extraordinary. It stretches space in one direction while compressing it in the perpendicular direction. One laser beam has a slightly longer journey, the other slightly shorter. The difference is minuscule beyond imagination, but when the beams recombine, the change in their timing creates a shift in that pattern of light and shadow. And that shift, invisible to the naked eye but clear as a bell to sophisticated detectors, is the signature of a gravitational wave. This is the principle behind LIGO, the Laser Interferometer Gravitational Wave Observatory. Two identical detectors, one in Louisiana and one in Washington State, each with arms stretching 2.5 miles in length, standing sentinel in the American landscape, listening for the universe's quietest whispers. But LIGO is not alone. Around the world, similar detectors have joined this cosmic symphony. Virgo in Italy, Kagra in Japan, and others planned for the future, creating a global network of gravitational wave observatories, each one a testament to human curiosity and ingenuity. For years, these detectors listened to silence. Day after day, month after month, they recorded the tiny vibrations of Earth itself, the rumble of distant traffic, the creaking of the buildings that housed them, the thermal noise of atoms jiggling in the mirrors. Scientists worked tirelessly to subtract all of this noise, to create a window so clear and quiet that they could hear the universe's most subtle songs. And then, on the 14th of September 2015, at exactly 9 hours, 50 minutes and 45 seconds UTC, something extraordinary happened. Both LIGO detectors, separated by nearly 2,000 miles, recorded the same signal within milliseconds of each other. It lasted only a fifth of a second, a brief chirp that rose in frequency and amplitude, like the sound of a drop of water hitting a still pond, but compressed into an impossibly short moment. That chirp was the death song of two black holes, each about 30 times more massive than our Sun, that had been locked in a spiraling dance for millions of years. In their final moments, as they plunged toward each other at speeds approaching the speed of light, they created ripples in space-time so powerful that even after travelling for 1.3 billion years across the universe, they were still strong enough to move LIGO's mirrors by a distance thousands of times smaller than the width of a proton. In that fraction of a second, those two black holes converted 3 times the mass of our Sun into pure gravitational waves, releasing more energy than all the stars in the observable universe combined. And yet by the time those waves reached Earth, they were so gentle that they passed through our planet, through our bodies, through every atom we're made of, as softly as a whisper. This detection, designated GW150914, was more than just a scientific triumph. It was the opening of an entirely new window into the universe, a new sense with which humanity could perceive the cosmos. For all of human history, we had studied the universe through light, the gentle glow of stars, the fierce radiation of quasars, the afterglow of the Big Bang itself. But light can be absorbed, scattered, blocked by dust and gas. Gravitational waves, by contrast, pass through everything virtually unimpeded. They carry information from places and events that no telescope could ever see, from the hearts of black holes, from the moments just after the Big Bang, from cosmic phenomena we haven't even imagined yet. Since that first detection, the symphony has grown richer and more complex. LIGO and its sister detectors have recorded dozens of gravitational wave events, more black hole mergers, each one unique, each one teaching us something new about these mysterious objects. They've detected the collision of 2 neutron stars, an event so energetic that it created gold, platinum, and other heavy elements, flinging them into space where they would eventually become part of planets and, perhaps, jewelry worn by lovers on distant worlds. Each detection is like learning a new word in the universe's vocabulary. The frequency tells us about the masses of the objects involved. The duration reveals how long their final dance lasted. The amplitude, the strength of the signal, whispers about how far away the event occurred. And the subtle variations in the waveform carry information about the spins of the objects, their orientations, even the fundamental properties of gravity itself. But perhaps the most beautiful thing about gravitational waves is what they represent, the universe's own memory. Every violent event, every cosmic collision, every accelerating mass sends ripples spreading outward through space-time. These waves carry the story of what happened, encoded in their frequency and amplitude, travelling at the speed of light until they reach some distant shore. We are that shore, and our detectors are learning to read the messages written in the geometry of space and time itself. As you lie there tonight, feeling the gentle pull of sleep, remember this: gravitational waves from countless cosmic events are washing over you right now. Waves from black holes that merged when the universe was young, from neutron stars spiraling together in distant galaxies, from phenomena we have yet to discover. They pass through you more gently than the softest breeze, carrying stories from the deepest corners of space and time. These waves connect us to the cosmos in the most intimate way imaginable. They don't just bring us information about distant events. They literally carry the space-time those events occurred in. When a gravitational wave passes through you, the space between your atoms expands and contracts ever so slightly. You become, for that brief moment, part of the cosmic story, woven into the same fabric that those distant black holes danced through billions of years ago. And this is just the beginning of our gravitational wave story. As our detectors become more sensitive, as we build new ones in space and on the ground, as we learn to listen more carefully to the universe's quietest songs, we'll hear new voices in this cosmic chorus. We'll detect the background hum of gravitational waves left over from the Big Bang itself, the universe's birth cry still echoing through space-time after nearly 14 billion years. We'll listen to the whispers of cosmic strings, if they exist, threading their way through the universe like cracks in reality itself. We'll hear the songs of primordial black holes, remnants from the universe's earliest moments, and perhaps even catch echoes of parallel universes brushing against our own in dimensions we can barely imagine. But tonight, as we drift deeper into this cosmic lullaby, let's focus on something wonderfully soothing, the sheer elegance of it all. Think about how remarkable it is that space and time, concepts so fundamental to our existence that we rarely question them, are not rigid and unchanging but fluid and dynamic. Space can stretch like warm honey, time can slow like a lazy river, and together they form a canvas on which the universe paints its most dramatic stories. When Einstein first proposed that space and time were woven together into a single fabric, it seemed almost mystical. How could empty space have properties? How could time be anything other than the steady tick of a cosmic clock? But gravitational waves prove that space-time is as real and tangible as any material substance. It can vibrate like a drum, ripple like water, and carry energy across the cosmos like waves on an ocean. This realization transforms how we see ourselves in the universe. We're not separate from space and time, observing them from the outside. We're embedded within them, part of the same continuous fabric that connects us to every star, every galaxy, every black hole. When those distant cosmic events send gravitational waves rippling through space-time, they're literally reshaping the geometry of the universe we inhabit. The space between your heartbeats, the time it takes for a thought to cross your mind, the distance between your fingers as they rest on your pillow, all of these are gently influenced by gravitational waves from events that happened billions of years ago in galaxies far, far away. And here's something that might help you sleep peacefully. These waves are incredibly democratic. They don't discriminate between rich and poor, young and old, human and butterfly. Every gravitational wave that passes through Earth affects everyone and everything equally. A wave that stretches the space in your bedroom also stretches the space in every other bedroom on the planet. We're all riding these cosmic ripples together, passengers on spaceship Earth as it sails through an ocean of gravitational waves. The mathematics behind gravitational waves is breathtakingly beautiful, though you needn't worry about understanding it to appreciate their wonder. Einstein's field equations, which describe how matter and energy curve spacetime, are written in the elegant language of differential geometry. They tell us that gravitational waves travel at exactly the speed of light, that they carry energy and momentum, that they can be focused and defocused by the curvature of space-time itself. But perhaps most beautifully, these equations tell us that gravitational waves are transverse, meaning they stretch and compress space perpendicular to their direction of travel. Imagine lying on your back, looking up at the ceiling, as a gravitational wave passes through you from head to toe. The wave doesn't change your height at all. Instead, it might make you ever so slightly wider for a moment, then ever so slightly narrower, then back to normal, all while making the room around you dance in the same gentle rhythm. This transverse nature is what allows our detectors to work so elegantly. LIGO's L-shaped design means that when a gravitational wave passes through, it stretches one arm while compressing the other, then reverses the effect half a cycle later. It's like the universe is gently massaging the detector, and we've learned to feel that massage through the interference patterns of laser light. The sensitivity required to detect these waves pushes the boundaries of what's technically possible. LIGO's mirrors must be isolated from vibrations so completely that they're essentially floating in perfect silence. The laser systems must be stable beyond anything ever built before. The data analysis requires computers to sift through months of data, looking for signals buried in noise like trying to hear a whisper in a thunderstorm. And yet, despite these incredible technical challenges, gravitational wave astronomy is rapidly becoming routine. What seemed impossible just a few decades ago is now an active field of research, with new detections announced regularly. Scientists are learning to read the universe's gravitational wave signatures, like astronomers learned to read the spectrum of starlight centuries ago. Each type of cosmic event produces its own characteristic gravitational wave signature, like a fingerprint written in the geometry of spacetime. When two black holes spiral together, they produce a chirp that rises in frequency and amplitude, growing stronger and faster as the objects draw closer until they merge in a final burst of gravitational radiation. The precise shape of this chirp tells us the masses of the black holes, how fast they were spinning, and how they were oriented when they collided. Neutron-star collisions produce different signatures, often longer and more complex, because these objects are not as perfectly smooth as black holes. They have crusts, magnetic fields, and complex internal structures that affect how they spiral together. When LIGO detected the first neutron-star merger in 2017, optical telescopes around the world swung into action, capturing the light from the explosion that followed. For the first time, humanity witnessed a cosmic event through both gravitational waves and traditional electromagnetic radiation, like having both eyes open to see the full depth and beauty of the scene. This multi-messenger astronomy, as scientists call it, is opening new chapters in our understanding of the cosmos. Gravitational waves tell us about the dynamics of the collision, the masses and spins of the objects involved, while light reveals the chemical elements created in the explosion, the temperature and density of the expanding fireball. Together, they provide a complete story of some of the most energetic events in the universe. But beyond the scientific discoveries, there's something profoundly moving about gravitational waves. They represent a kind of cosmic empathy, the universe's way of sharing its most dramatic moments with anyone patient enough to listen. When you really think about it, every gravitational wave detector on Earth is like a giant ear pressed against the cosmos, listening for the heartbeat of distant worlds. And that heartbeat is surprisingly varied and musical. Scientists often convert gravitational wave data into sound waves so they can listen to the signals directly. The chirp of merging black holes sounds hauntingly beautiful, like a drop of water falling into a deep well. Neutron-star collisions produce longer, more complex sounds, sometimes described as resembling bird songs or electronic music. Each detection adds a new note to the universe's gravitational symphony. There's also something wonderfully humbling about gravitational waves. They remind us that space and time, which seem so solid and dependable in our daily lives, are actually dynamic and responsive to the matter and energy they contain. The universe is not a static stage on which events unfold, but an active participant in its own story, vibrating with the echoes of everything that has ever happened within it. As our detectors become more sensitive, we're beginning to hear fainter and more distant signals. Future gravitational wave observatories will be able to detect events from the very early universe. Perhaps even the gravitational waves produced during cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. These primordial gravitational waves would carry information about the universe when it was younger than a single heartbeat, opening a window into physics at energy scales we could never reproduce in laboratories. Space-based gravitational wave detectors, like the planned LIGO mission, will listen for different types of signals altogether. With arms millions of kilometers long, formed by laser beams connecting spacecraft in orbit around the Sun, these detectors will be sensitive to gravitational waves, with much lower frequencies than Earth-based instruments can detect. They'll hear the slow, steady signals from massive black holes at the centers of galaxies, the whispers of white dwarf stars spiraling together over millions of years, and perhaps signals from cosmic phenomena we haven't even imagined yet. But you don't need to wait for future detectors to experience gravitational waves. They're passing through you right now, as they have been every moment of your life. Every time your heart beats, every time you take a breath, every time you shift position as you drift towards sleep, you're doing so within a universe that is constantly vibrating with gravitational waves from across the cosmos. These waves connect you to the deepest mysteries of existence. They carry information about the nature of gravity itself, about the fabric of spacetime, about the most extreme environments in the universe. They whisper stories of black holes so massive that they bend light into impossible spirals, of neutron stars so dense that a teaspoon of their material would weigh as much as a mountain, of cosmic events so energetic that they outshine entire galaxies for brief, brilliant moments. And yet, for all their cosmic significance, gravitational waves remain gentle and unobtrusive. They pass through your body billions of times each second, from sources both near and unimaginably distant, without disturbing so much as a single atom. They're like cosmic ghosts, carrying the memories of distant events while barely interacting with the present world. This ghostly quality makes gravitational waves perfect messengers for studying the universe's most hidden secrets. Light can be absorbed by dust, scattered by gas, or blocked by solid objects. But gravitational waves pass through almost everything as if it weren't there at all. They travel to us directly from the hearts of black holes, from the cores of neutron stars, from regions of space where light has never shone. In a way, gravitational waves are the universe's most honest form of communication. They can't be faked or distorted or hidden behind cosmic dust clouds. When we detect a gravitational wave signal, we know with absolute certainty that somewhere in the cosmos, massive objects really did accelerate and dance and merge, sending ripples through spacetime that have now reached our quiet corner of the universe. As you settle deeper into comfort tonight, let this thought wash over you like a warm tide. You are connected to the cosmos in ways both profound and gentle. Gravitational waves from the birth of black holes, from the collision of neutron stars, from events we have yet to discover, are flowing through you at this very moment. You are part of the same space-time fabric that trembles with the echoes of cosmic catastrophes and whispers with the songs of distant worlds. These waves don't just carry information about distant cosmic events, they carry the very essence of those events, the actual space-time in which they occurred. When a gravitational wave from a black hole merger passes through you, you're literally feeling the same curvature of space-time that those massive objects created in their final dance billions of years ago. It's as if the universe has a memory, written not in books or digital files, but in the geometry of space and time itself. Think of it this way. Every gravitational wave is like a message in a bottle, cast into the cosmic ocean by some distant event and carried on currents of space-time until it washes up on the shores of Earth. But unlike a message in a bottle, which contains only information, a gravitational wave is the actual medium in which the message was written. The wave doesn't just tell us about the collision of two black holes. It carries within itself the very space-time that those black holes warped and twisted in their final moments. This creates a beautiful paradox that might help you drift into peaceful sleep. The most violent events in the universe, explosions that release more energy in seconds than our sun will produce in its entire lifetime, reach us as the gentlest possible touch. By the time these cosmic shockwaves travel across billions of light years, they arrive at Earth with all the force of a feather landing on silk. It's as if the universe has a built-in mechanism for turning cosmic violence into cosmic poetry. And there's something wonderfully democratic about this cosmic poetry. Gravitational waves don't discriminate based on wealth, status, or species. The same wave that passes through a sleeping child also passes through the family cat, the houseplants on the windowsill, and every grain of sand on every beach. We're all equal participants in this cosmic dance, all riding the same gentle ripples through space-time together. The mathematics that describe these waves reveal something even more beautiful. Unlike sound waves, which need air to travel, or water waves, which need water, gravitational waves need nothing but space and time themselves. They are waves in the very medium of existence, ripples in the fabric from which reality is woven. In a sense, gravitational waves are the most fundamental form of wave in the universe because they are waves of the universe itself. Scientists have discovered that these waves come in many different flavors, each with its own signature rhythm and melody. The quick, sharp chirp of merging black holes sounds very different from the long, slow song of massive black holes orbiting each other at the centers of galaxies. Neutron-star collisions produce complex harmonies that can last for minutes, while the theoretical cosmic strings we mentioned earlier would create single, pure tones that stretch across the cosmos like the longest possible guitar strings. But perhaps the most intriguing gravitational waves we might someday detect are the ones left over from the Big Bang itself. These primordial waves, if they exist, would be the universe's birth cry, still echoing through space-time after nearly 14 billion years. They would carry information about the first moments of cosmic inflation, when the universe expanded faster than the speed of light, stretching quantum fluctuations into the seeds of galaxies and stars. Imagine that, waves created when the universe was smaller than a grain of sand, now washing over you as you prepare for sleep. These waves would have traveled through the entire history of the cosmos, witnessing the formation of the first stars, the birth of galaxies, the creation of heavy elements in stellar furnaces, and the long, slow process that eventually led to planets, life, and consciousness. They would be the ultimate cosmic messengers, carrying stories from a time when the universe itself was learning how to exist. The detectors we've built to listen for these whispers are marvels of human ingenuity that would seem like magic to scientists from just a few decades ago. LIGO's mirrors are suspended by systems so sophisticated they can isolate the mirrors from every possible vibration except gravitational waves themselves. The laser beams that travel between these mirrors are so stable that they can measure changes in distance smaller than 1/10,000th the width of a proton. That's like measuring the distance from Earth to the nearest star to an accuracy smaller than the width of a human hair. But the real magic happens in the data analysis. When a gravitational wave passes through LIGO, it creates a signal buried in noise from thousands of different sources: distant earthquakes, passing trucks, thermal motion of atoms in the mirrors, even quantum fluctuations in the laser light itself. Finding a gravitational wave signal in all this noise is like trying to hear a whisper in a thunderstorm while wearing earplugs. It requires computers to search through months of data using sophisticated algorithms that can recognize the characteristic signatures of different types of cosmic events. Each detection is a small miracle of engineering and physics working together. When scientists first saw the signal from GW150914, that first gravitational wave detection, some of them initially thought it might be a joke or a test signal that someone had secretly injected into the system. The signal was almost too perfect, too clear, too much like what Einstein's equations predicted it should look like. It took weeks of careful analysis to confirm that they had really heard the universe singing. Since then, each new detection has added to our understanding of how the cosmos works at its most extreme edges. We've learned that black holes can spin incredibly fast, rotating hundreds of times per second. We've discovered that neutron-star collisions are the universe's primary factories for creating gold, platinum, and other heavy elements. We've seen that massive black holes can form through the merger of smaller ones, growing like cosmic snowballs as they accumulate mass over billions of years. But beyond the specific scientific discoveries, gravitational wave astronomy has given us something even more precious, a new sense of our place in the universe. We are no longer passive observers of cosmic events, studying them only through the ancient light that reaches our telescopes. We are active participants in the gravitational symphony, our bodies and our planet, and our entire solar system responding to the rhythm of distant cosmic dances. This participation is incredibly intimate. When a gravitational wave passes through you, it doesn't just carry information past you like a radio signal. It actually changes the geometry of the space you occupy. The distance between your head and your feet remains the same, but the space between your atoms expands and contracts in rhythm with waves that began their journey billions of years ago in galaxies so distant their light has not yet reached Earth. And here's something that might fill you with wonder as you drift towards sleep. Every gravitational wave detector on Earth is essentially a giant antenna for listening to the universe's heartbeat. When LIGO in Louisiana and LIGO in Washington detect the same signal within milliseconds of each other, they're confirming that we've heard something real, something that really happened in the depths of space and time. The fact that the same wave reaches both detectors, traveling at the speed of light across thousands of miles, proves that these ripples in space-time are as real and fundamental as any other aspect of physical reality. Future gravitational wave detectors will be even more sensitive, able to hear whispers from across the entire observable universe. The Cosmic Explorer, planned for construction in the coming decades, will have arms 10 kilometers long and sensitivity so exquisite it could detect gravitational waves from the merger of black holes anywhere in the visible universe. Einstein Telescope, planned for construction underground in Europe, will be so quiet and so sensitive that it will hear gravitational waves constantly, creating a continuous soundtrack of cosmic events happening across space and time. But even these incredible instruments pale in comparison to space-based detectors like LISA, the Laser Interferometer Space Antenna. LISA will consist of 3 spacecraft flying in formation millions of kilometers apart, connected by laser beams that can detect gravitational waves with wavelengths as long as the diameter of Earth's orbit. These space-based detectors will open an entirely new range of the gravitational wave spectrum, listening for signals that Earth-based instruments could never hear. LISA will be sensitive to gravitational waves from massive black holes at the centers of galaxies, objects millions of times more massive than our Sun, that create gravitational waves when they spiral together over millions of years. These waves will have frequencies so low that a single oscillation might take hours or days to complete. Listening to these ultra-low frequency waves will be like hearing the universe's deepest bass notes, the fundamental tones that underlie all the higher frequency cosmic music we detect with ground-based instruments. These space-based detectors will also be able to hear gravitational waves from white dwarf stars, the dense remnants of stars like our Sun that have exhausted their nuclear fuel. When 2 white dwarfs orbit each other closely, they create gravitational waves with frequencies in the millihertz range, far too low for LIGO to detect. LISA will hear thousands of these systems throughout our galaxy, creating a kind of gravitational wave background that will teach us about the population and evolution of stellar remnants in the Milky Way. But perhaps most excitingly, space-based detectors might be sensitive enough to hear the gravitational wave background from the Big Bang itself. This cosmic background of gravitational waves would be analogous to the cosmic microwave background radiation that we can see with radio telescopes, but it would carry information from much earlier in the universe's history. While the cosmic microwave background shows us the universe as it was about 380,000 years after the Big Bang, primordial gravitational waves could carry information from the first tiny fraction of a second after the universe began. These primordial waves would be incredibly faint, requiring detectors of extraordinary sensitivity to detect them. But if we could hear them, they would tell us about the physics of the universe at energy scales far beyond anything we could ever create in particle accelerators. They might reveal evidence for cosmic inflation, the rapid expansion that occurred in the first moments after the Big Bang. They might tell us about extra dimensions of space that we can't directly perceive. They might even carry signatures of the quantum nature of gravity itself. As you lie there tonight, surrounded by the gentle hum of gravitational waves from across the cosmos, you might wonder what it all means for your daily life. After all, these waves are so weak that they have no measurable effect on your body, your health, or your immediate environment. They don't change the weather, influence your mood, or affect the growth of plants. In practical terms, you could live your entire life without ever knowing that gravitational waves exist. But in a deeper sense, gravitational waves connect you to the universe in the most profound way possible. They remind us that space and time are not empty voids, but active, dynamic aspects of reality that respond to the presence of matter and energy. They show us that we live in a universe where every event, no matter how distant, sends ripples through the fabric of existence that eventually reach every other point in space and time. This cosmic connectivity has philosophical implications that have captivated thinkers since Einstein first predicted gravitational waves. If space-time is truly a unified fabric, and if gravitational waves propagate through this fabric at the speed of light, then in some sense, every event in the universe eventually influences every other location in the universe. The collision of two black holes 13 billion years ago sends gravitational waves that are passing through your bedroom right now. The formation of the first stars after the Big Bang created ripples in space-time that are still propagating outward, still carrying information about those ancient stellar nurseries. This means that you are literally connected to every star that has ever shone, every black hole that has ever formed, every cosmic event that has ever occurred. The connection is incredibly weak, weaker than the gentlest breeze or the softest whisper, but it is real and fundamental. In the language of physics, we say that you are coupled to the gravitational field of the entire universe, and that field carries within it the memory of everything that has ever happened. There's something both humbling and comforting about this cosmic perspective. On one hand, it reminds us how small we are compared to the vast scales of space and time on which gravitational waves operate. The energies involved in creating detectable gravitational waves are so enormous that they dwarf anything in human experience. A typical black hole merger releases more energy in gravitational waves in its final second than all the stars in our galaxy produce in light. But on the other hand, this cosmic connection reminds us that we are not separate from the universe, but part of it in the most fundamental way possible. The atoms in your body were forged in the cores of ancient stars, and those stars were born from gas clouds that were shaped by gravitational waves from even earlier cosmic events. The gravitational waves passing through you right now are part of the same space-time fabric that your body occupies. In a very real sense, you and the gravitational waves are made of the same stuff, curved space-time, the fundamental medium of existence itself. This perspective might help you sleep more peacefully tonight. Instead of seeing yourself as isolated and alone in a vast, empty universe, you can think of yourself as intimately connected to everything that has ever existed. Every breath you take occurs within space-time that is gently vibrating with gravitational waves from across the cosmos. Every heartbeat happens in synchrony with the rhythm of distant cosmic dances that began billions of years before Earth even existed. And tomorrow, when you wake up, those same gravitational waves will still be passing through you, carrying new stories from the depths of space and time. Somewhere in the universe, new black holes will be spiraling together, new neutron stars will be colliding, new cosmic events will be sending fresh ripples through the fabric of existence. Our detectors will be listening, ready to decode these messages from the cosmos and add new chapters to humanity's growing understanding of the gravitational wave universe. But you don't need sophisticated detectors to appreciate the wonder of gravitational waves. You need only remember that you are part of a universe where space and time themselves can dance, where the most distant events can touch you in the gentlest possible way, where the fabric of reality itself carries the songs of cosmic creation and destruction across billions of years and billions of light years to reach you here, now, in this quiet moment as you prepare for sleep. So rest well tonight, knowing that you are cradled not just in your bed but in the loving embrace of space-time itself, gently rocking with gravitational waves from the farthest corners of the universe, connected to every star and galaxy through the most subtle and beautiful force in all of physics. The beauty of gravitational wave detection lies not just in the cosmic events we've discovered, but in how we've learned to listen. Each detector around the world has its own personality, its own way of interpreting the universe's whispers. LIGO in Louisiana sits in a landscape of cypress swamps and bayous, where the humid air shimmers with heat and the ground trembles with the footsteps of passing alligators. Yet somehow, through layers of vibration isolation that would make a watchmaker weep with envy, this detector can sense the passage of gravitational waves that barely disturb the vacuum of space. Meanwhile, LIGO in Washington rests in the high desert, where the air is dry and the nights are clear enough to see the Milky Way stretching across the sky like a river of ancient light. The contrast is poetic. Two instruments separated by a continent, yet working together as a single cosmic ear, listening for the same ethereal signals from events that happened when the universe was young. When both detectors record the same gravitational wave signal, scientists can do something rather magical with the timing difference between the arrivals. Since gravitational waves travel at the speed of light, the few milliseconds of delay between Louisiana and Washington can tell us roughly where in the sky the signal came from. It's like triangulation, but with the most precise timing measurements ever made, using the entire continental United States as a baseline. This process has led to some of the most exciting discoveries in modern astronomy. When LIGO detected that first neutron-star collision in 2017, the gravitational wave data told astronomers approximately where to look in the sky. Within hours, telescopes around the world were turning toward that patch of darkness, and what they saw was breathtaking. A kilonova, an explosion so bright it outshone its entire host galaxy, glowing with the light of newly forged gold and platinum atoms. For the first time in history, humanity witnessed a cosmic event through both gravitational waves and light, like suddenly gaining stereoscopic vision for astronomical phenomena. The gravitational waves told the story of the collision itself, the final spiral dance of two neutron stars as they approached each other at a significant fraction of the speed of light. The optical telescopes revealed the aftermath, the expanding fireball of exotic matter cooling and condensing into heavy elements that would eventually become part of new star systems, new planets, perhaps even new forms of life. This multi-messenger approach to astronomy has revealed something beautiful about the universe's storytelling methods. Different types of waves carry different chapters of the same cosmic tale. Gravitational waves show us the dynamics, the motion, the dance of massive objects through space-time. Light reveals the chemistry, the temperature, the composition of matter in its most extreme states. Radio waves whisper about magnetic fields and particle acceleration. X-rays shout about the hottest, most energetic processes in the cosmos. When we combine all these messengers, we get something approaching a complete narrative of cosmic events. It's like reading a story that's been scattered across different books, different languages, different forms of expression, and finally having the key to translate them all into a unified tale. The universe, it seems, is quite the storyteller, but it prefers to tell its stories across the entire electromagnetic spectrum and through the fabric of space-time itself. But there's something even more profound happening here. Each gravitational wave detection is teaching us that Einstein's century-old equations continue to describe reality with almost uncanny precision. Every chirp, every merger, every cosmic collision we detect matches the predictions of general relativity to extraordinary accuracy. It's as if Einstein, working alone in his study with nothing but paper, pen, and pure thought, somehow managed to overhear conversations between black holes that wouldn't happen for another billion years. This remarkable agreement between theory and observation gives us confidence that we truly understand something fundamental about how the universe works. When LIGO detects a gravitational wave, scientists can work backwards from the signal to determine the masses of the colliding objects, their spins, their orientations, even their distance from Earth. These calculations rely entirely on Einstein's equations, and the fact that they consistently produce sensible, consistent results is a testament to the power of mathematical physics. Yet even as we celebrate these successes, gravitational wave astronomy continues to surprise us. Some of the black holes we've detected are more massive than we thought possible. Some spin faster than our models predicted. Some mergers happen more frequently than we expected, while others are rarer than our theories suggested. Each detection refines our understanding, but also opens new questions about how these exotic objects form and evolve. One of the most intriguing puzzles involves the gap between neutron stars and black holes. For decades, astronomers thought there was a clear distinction. Neutron stars max out at about 2.5 times the mass of our Sun, while the smallest black holes are at least 5 solar masses. But gravitational wave detections have started to fill in that gap, revealing objects that might be the most massive neutron stars ever found, or perhaps the lightest black holes, or maybe something entirely new that we don't yet understand. These mysterious objects challenge our understanding of matter under extreme conditions. What happens to atoms when they're squeezed to densities beyond anything we can create on Earth? How does matter behave when gravity becomes so strong that it begins to warp the very concept of space and time? Gravitational waves from neutron-star mergers carry information about these extreme states of matter, encoded in the subtle variations of their waveforms. Scientists have learned to read these gravitational wave signatures like a cosmic form of seismology. Just as earthquakes create seismic waves that tell us about Earth's internal structure, the gravitational waves from colliding neutron stars reveal the properties of matter at nuclear densities. The stiffness of the neutron star's crust, the fluidity of its core, the strength of its magnetic field, all of these properties leave their fingerprints in the gravitational waves produced when two such objects spiral together. This has opened an entirely new field of study, nuclear physics on cosmic scales. Laboratory experiments can tell us how atomic nuclei behave under normal conditions, but the cores of neutron stars represent conditions so extreme that we can only study them through gravitational wave astronomy. In a sense, every neutron star collision is a cosmic laboratory experiment, probing the fundamental properties of matter at densities where our earthbound intuitions completely fail. The implications extend beyond pure physics into the realm of cosmic chemistry. Those heavy elements created in neutron star collisions, the gold and platinum and rare earth metals that make modern technology possible, were once thought to be produced primarily in supernova explosions. But gravitational wave astronomy has revealed that neutron star mergers might be equally important, perhaps more so, in seeding the universe with these precious materials. Think about that for a moment as you settle deeper into comfort. The gold in any jewelry you might wear, the rare earth elements in the device you're listening to this on, the heavy metals that make our technological civilization possible, many of these atoms were forged in the unimaginably violent collision of two neutron stars billions of years ago. The gravitational waves from that ancient collision have long since passed through our solar system, but the atoms it created have found their way into planets, into life, into you. This cosmic recycling program has been operating for billions of years, with each generation of stars and stellar explosions adding new elements to the universe's chemical inventory. Gravitational wave astronomy is helping us understand this process in unprecedented detail, revealing how often these cosmic furnaces operate, how much material they produce, and how it gets distributed throughout the cosmos. But the story of gravitational waves extends far beyond individual cosmic events. As our detectors become more sensitive and our observation time lengthens, we're beginning to glimpse something even more fundamental: the gravitational wave background of the universe itself. Just as there's a background of microwave radiation left over from the Big Bang, there should be a background of gravitational waves created by the countless cosmic events that have occurred throughout cosmic history. This gravitational wave background would be incredibly faint, requiring detectors far more sensitive than anything we have today. But if we could measure it, it would tell us about the statistical properties of cosmic events throughout the universe's entire history. How often do black holes merge? How many neutron-star collisions have occurred since the first stars formed? What was the universe like during its first few moments, when quantum fluctuations were stretched by cosmic inflation into the seeds of everything we see today? The search for this cosmic background is one of the holy grails of gravitational wave astronomy. It would be like hearing the universe's entire symphony at once, all the cosmic events that have ever occurred blending together into a single incredibly complex chord. Detecting and analyzing this background would require computational techniques that push the boundaries of what's possible, searching for patterns and correlations in signals so weak they're barely distinguishable from noise. Yet even as we reach toward these ultimate goals, gravitational wave astronomy continues to deliver surprises closer to home. Our own galaxy, the Milky Way, is home to millions of binary star systems, where two objects orbit each other closely enough to produce gravitational waves. Most of these are too weak for current detectors to sense individually, but future space-based observatories like LIGO will hear them as a constant chorus of gravitational wave signals. Imagine listening to the gravitational wave soundtrack of our entire galaxy. LIGO will detect tens of thousands of these galactic binary systems, each one contributing its own note to a cosmic symphony that has been playing for billions of years. The loudest signals will come from the most exotic systems, pairs of white dwarf stars spiraling together over millions of years, neutron stars in tight orbits around black holes, perhaps even stranger configurations that we haven't yet imagined. This galactic gravitational wave survey will revolutionize our understanding of stellar evolution and the structure of our cosmic neighborhood. We'll learn how binary systems form and evolve, how often they merge, what happens to the surviving remnants. We'll map the distribution of compact objects throughout the galaxy, revealing the fossil record of stellar death and rebirth written in the geometry of spacetime itself. But perhaps most remarkably, gravitational wave astronomy is beginning to reveal the universe's deepest secrets about the nature of gravity itself. Einstein's general relativity has passed every test we've thrown at it for over a century, but gravitational waves offer a completely new way to probe gravity in its strongest possible manifestations. When two black holes merge, they create gravitational fields billions of times stronger than anything we experience on Earth, in regimes where Einstein's equations are pushed to their absolute limits. So far, every gravitational wave detection has confirmed Einstein's predictions with remarkable precision. The waves arrive at exactly the speed of light. They carry exactly the energy that general relativity predicts. They interact with our detectors in precisely the way Einstein's equations suggest they should. It's a triumph of theoretical physics that would have seemed impossible just a few decades ago. Yet scientists continue to search for subtle deviations from Einstein's theory, tiny discrepancies that might reveal new physics beyond general relativity. Some theories of quantum gravity predict that gravitational waves might be accompanied by other types of waves, exotic signals that would appear as small corrections to Einstein's predictions. Others suggest that the fundamental constants of nature might vary slightly with time, creating tiny signatures in gravitational wave signals that have traveled for billions of years. These searches require analyzing gravitational wave data with extraordinary care, looking for deviations from Einstein's predictions that might be millions of times smaller than the signals themselves. It's like listening to a symphony and trying to detect whether one instrument is playing a note that's a tiny fraction of a semitone off key. The computational challenges are immense, but the potential rewards are revolutionary. Evidence for new physics beyond our current understanding of gravity, space, and time. As you drift towards sleep tonight, consider the magnificent irony of our situation. We live in an era when the universe's most violent events reach us as the gentlest possible touches, when cosmic catastrophes billions of light years away announce themselves through changes in distance smaller than a fraction of a proton's width. We've built instruments so sensitive they can detect the whispers of space-time itself, yet these same instruments must be protected from every vibration, every thermal fluctuation, every quantum uncertainty that might mask the signals we're seeking. This delicate balance between cosmic violence and terrestrial precision, between the largest scales in the universe and the smallest measurements we can make, captures something essential about the human quest to understand our place in the cosmos. We are tiny beings on a small planet orbiting an ordinary star in an unremarkable galaxy. Yet through ingenuity and persistence, we've learned to eavesdrop on conversations between black holes, to decode messages written in the fabric of space-time itself. The gravitational waves passing through you right now carry stories from across the universe and across cosmic time. Some began their journey when the universe was a fraction of its current age, when the first stars were just beginning to shine. Others started their trip when Earth was a molten ball of rock, long before life emerged from the primordial oceans. Still others left their sources when dinosaurs roamed our planet, or when the first humans looked up at the stars and wondered about their place in the cosmos. All of these waves, from all of these different epochs, are converging on you at this moment, carrying their messages through the darkness of space and the vastness of time to reach you here, now, as you prepare for sleep. They pass through your body more gently than the softest breeze, yet they connect you to the most energetic events in the universe's history. They are simultaneously the most powerful forces in existence and the most subtle influences you will ever encounter. This paradox of power and gentleness, of cosmic significance and intimate subtlety, makes gravitational waves perfect companions for the threshold of sleep. Like the best lullabies, they are both meaningful and soothing, both connected to vast stories and immediately present in your personal experience. They remind us that we live in a universe where violence becomes poetry, where chaos becomes music, where the most distant events can touch us in the most tender ways. Tomorrow, scientists around the world will wake up to new gravitational wave data, new signals from the cosmic deep that arrived during the night. They'll analyze these signals with sophisticated algorithms, extract from them the masses and spins and distances of exotic objects, add new entries to the growing catalogue of gravitational wave sources. They'll continue the grand human project of learning to read the universe's stories, written in a language older than light, carried by messengers that have travelled since the dawn of time. But tonight, as those same waves flow through your resting body, you don't need to analyze or catalogue or understand them. You need only to rest in the knowledge that you are part of something larger, something beautiful, something that connects every atom in your body to every star in the sky through the gentle medium of curved space-time. You are riding gravitational waves from across the cosmos, and they are carrying you, along with everyone and everything else on Earth, through the vast ocean of existence toward whatever wonders tomorrow might bring. Sleep well, fellow traveller, knowing that the universe is singing you its softest, most ancient lullabies, written in the language of gravity itself, delivered by waves that have crossed unimaginable distances to rock you gently toward your dreams. And as these cosmic lullabies wash over you, there's something wonderfully poetic about the fact that we're still only at the very beginning of this gravitational wave story. Each detection opens new questions, reveals new mysteries, points toward phenomena we haven't even begun to imagine. It's like learning the first few words of a language that the universe has been speaking for nearly 14 billion years. A language written not in sounds or symbols, but in the very geometry of existence itself. Consider the remarkable journey that brought us to this moment. For most of human history, we experience the universe through our basic senses, seeing the light from stars, feeling the warmth of the sun, watching the moon's phases mark the passage of time. Then we built telescopes and opened our eyes to wavelengths beyond the visible spectrum, revealing radio galaxies and X-ray binaries and gamma-ray bursts. Each new window into the electromagnetic spectrum showed us a universe stranger and more wonderful than we had previously imagined. But gravitational waves represent something fundamentally different from all forms of light. They don't emerge from the surface of objects or from the interaction of matter with electromagnetic fields. They arise from the motion of space-time itself, from the dance of massive objects through the fabric of reality. When we detect gravitational waves, we're not seeing light that has been emitted, absorbed, scattered, or reflected. We're feeling the actual geometry of the universe as it vibrates with the memory of distant cosmic events. This gives gravitational wave astronomy a kind of purity that's both scientifically valuable and aesthetically beautiful. The waves carry information directly from their sources without the complicated processing that affects light traveling through interstellar space. They don't get dimmed by cosmic dust, reddened by the expansion of the universe, or absorbed by intervening gas clouds. They simply propagate outward from their sources, carrying their messages with pristine clarity across billions of years and billions of light years. This pristine quality has already led to some surprising discoveries about the population of black holes in our universe. Before LIGO began operating, astronomers knew of only a few dozen stellar mass black holes, all detected through their gravitational influence on nearby companion stars. But gravitational wave detections have revealed a hidden population of black holes that don't have luminous companions, black holes that were completely invisible to traditional astronomy, but announce themselves clearly when they collide with other compact objects. These solitary black holes appear to be much more common than we previously thought, and some of them are more massive than theoretical models predicted. The most massive stellar black holes detected through gravitational waves challenge our understanding of how stars evolve and die. According to standard models of stellar evolution, stars above a certain mass should produce black holes no more massive than about 45 times our Sunday. Yet LIGO has detected black holes nearly twice that massive, suggesting that our models of stellar death are incomplete. Even more intriguingly, some gravitational wave detections hint at the existence of primordial black holes, exotic objects that might have formed not from the collapse of massive stars, but from extreme density fluctuations in the early universe. These ancient black holes would be fossils from cosmic inflation, remnants of the universe's first moments that have survived for nearly 14 billion years. If primordial black holes exist, they could help explain some of the universe's most persistent mysteries, including the nature of dark matter itself. The search for primordial black holes through gravitational wave astronomy represents a beautiful convergence of the very large and the very small, connecting observations of cosmic collisions with theories of quantum gravity and particle physics. It's possible that some of the gravitational waves we're detecting today were produced by the collision of objects that formed when the universe was less than a second old, carrying information about physics at energy scales far beyond anything we could ever reproduce in terrestrial laboratories. But gravitational waves also promise to reveal secrets much closer to home. Our own galaxy contains millions of compact binary systems, pairs of white dwarfs, neutron stars, and black holes that are slowly spiraling together under the influence of gravitational wave radiation. Most of these systems won't merge for millions or billions of years, but they're all producing gravitational waves right now, creating a kind of galactic background chorus that future detectors will hear as a constant hum. This galactic gravitational wave background will be incredibly rich in information. By analyzing the frequency spectrum of this background, astronomers will be able to determine the number and types of compact binaries throughout the Milky Way. We'll learn about the birth rate of neutron stars and black holes, the distribution of orbital periods and eccentricities, the role of stellar evolution in creating these exotic systems. It will be like taking a census of the galaxy's most extreme residents, counting populations that are completely invisible to optical telescopes. Space-based gravitational wave detectors like LISA will be particularly well suited for this type of galactic archaeology. With arms millions of kilometers long, LISA will be sensitive to gravitational waves with periods of hours to days, exactly the range produced by the wide binary systems that populate our galaxy. The detector will be so sensitive that it will individually resolve thousands of these galactic sources, each one contributing its own thread to the complex tapestry of gravitational waves that surrounds us. But perhaps the most exciting prospect for gravitational wave astronomy lies in its potential to probe the universe's earliest moments. During cosmic inflation, the rapid expansion that occurred in the first tiny fraction of a second after the Big Bang, quantum fluctuations in the gravitational field would have been stretched to cosmic scales, creating a background of primordial gravitational waves. These ancient waves would still be propagating through the universe today, carrying information about conditions when the cosmos was younger than the time it takes light to travel across a proton. Detecting primordial gravitational waves would be like finding the universe's birth certificate, direct evidence for the inflationary epoch that shaped the large-scale structure we see today. The frequency spectrum of these waves would reveal the energy scale at which inflation occurred, providing crucial clues about the physics of the very early universe. It might even tell us about the existence of extra dimensions, the nature of the inflaton field that drove expansion, or the connection between gravity and quantum mechanics at the most fundamental level. The technical challenges of detecting primordial gravitational waves are enormous. These signals would be incredibly weak, perhaps millions of times fainter than the astrophysical sources we detect today. They would be buried beneath noise from countless other sources, instrumental vibrations, thermal fluctuations, quantum uncertainties, and the gravitational wave signals from astrophysical objects throughout the universe. Extracting primordial signals from this cacophony would require detector sensitivities and data analysis techniques that push far beyond our current capabilities. Yet the potential rewards are so great that scientists are already beginning to design the next generation of gravitational wave observatories specifically to search for these cosmic fossils. Concepts like the Big Bang Observer, a space-based detector with sensitivity orders of magnitude beyond LISA, could potentially hear the echo of inflation itself. The Cosmic Explorer and Einstein Telescope, ground-based detectors with arms tens of kilometers long, might be sensitive enough to detect primordial waves in certain frequency ranges. These future instruments will also open entirely new windows into astrophysical phenomena. They'll detect gravitational waves from stellar core collapse, the moment when a massive star's core implodes to form a neutron-star or black hole. They'll hear the gravitational wave signatures of cosmic strings, if these theoretical objects exist, one-dimensional defects in spacetime that would create distinctive gravitational wave patterns as they oscillate and interact. They might even detect gravitational waves from more exotic sources, evaporating primordial black holes, releasing their energy in bursts of gravitational radiation, or phase transitions in the early universe when different fields settled into their current states. Each new type of source would add its voice to the growing gravitational wave symphony, revealing aspects of the cosmos that remain completely hidden from electromagnetic observations. But as we dream about these future discoveries, it's worth remembering that gravitational wave astronomy is still in its infancy. We've been detecting these cosmic ripples for less than a decade, and already they've revolutionized our understanding of black holes, neutron stars, and the fundamental nature of space-time. As our detectors become more sensitive, as we build new instruments in space and on the ground, as we develop more sophisticated analysis techniques, Who knows what wonders await discovery? Perhaps we'll find that the universe is filled with gravitational wave sources we haven't even imagined yet. Perhaps we'll discover that space-time itself has properties that Einstein never suspected. Perhaps we'll hear signals from parallel universes, or from dimensions beyond the three of space and one of time that define our everyday experience. The history of astronomy suggests that whenever we open a new window into the cosmos, we find phenomena stranger and more beautiful than we ever anticipated. There's something deeply moving about this ongoing expansion of human perception. Just as our ancestors learned to see beyond the narrow band of visible light, revealing the radio universe and the X-ray sky and the gamma-ray cosmos, we are now learning to feel the universe through gravitational waves. We're developing a new sense, a cosmic sense of touch that allows us to feel the vibrations of space-time itself. This new sense is teaching us that the universe is far more dynamic and interconnected than we previously imagined. Every massive object in motion contributes to the cosmic gravitational wave background. Every accelerating mass, from orbiting planets to colliding galaxies, sends ripples through space-time that eventually reach every other point in the universe. We live in a cosmos that is constantly vibrating, constantly singing, constantly sharing the stories of its most dramatic events through the medium of curved space-time. And you are part of this cosmic symphony. As you lie there tonight, gravitational waves from hundreds of different sources are passing through your body simultaneously. Waves from binary pulsars in our galaxy, waves from black hole mergers in distant clusters, waves from neutron-star collisions that occurred when the universe was half its current age. Each wave carries its own story, its own frequency signature, its own message about the cosmic event that created it. The remarkable thing is that all these waves pass through the same space, the same time, the same you, without interfering with each other in any destructive way. Unlike sound waves, which can cancel each other out when they meet, gravitational waves simply add together, creating a complex but coherent pattern of space-time curvature. It's as if the universe has an infinite capacity for stories, an unlimited bandwidth for carrying messages across cosmic distances and cosmic time. This non-interference property of gravitational waves means that the cosmic gravitational wave background contains information about every significant mass acceleration that has ever occurred in the observable universe. In principle, if we had perfect detectors and infinite computational power, we could decompose this background into its individual components and reconstruct the entire history of cosmic violence. Every black hole merger, every neutron-star collision, every stellar core collapse that has ever occurred. Of course, we'll never have perfect detectors or infinite computational power, but the aspiration itself is beautiful. The idea that the universe keeps perfect records of its own history, written in the geometry of space-time and carried by gravitational waves that never decay or disappear, gives a kind of permanence to even the most transient cosmic events. Nothing is ever truly lost in a universe where space-time itself serves as an eternal memory. This cosmic memory is already beginning to reveal patterns that surprise us. The rate of black hole mergers appears to be higher than most theoretical models predicted, suggesting that these exotic objects form more frequently or survive longer than we thought. The mass distribution of merging black holes shows unexpected features, with some mass ranges more common than others in ways that challenge our understanding of stellar evolution. Similarly, the detection of neutron-star mergers has confirmed that these events are indeed major producers of heavy elements. But the rates we observe suggest that the universe's inventory of gold, platinum, and rare earth metals might be replenished more quickly than we previously thought. This has implications for understanding when and where planets capable of supporting complex chemistry and potentially life might form throughout cosmic history. These discoveries are already influencing how we think about our own cosmic context. The elements that make Earth-like planets possible, the heavy metals that enable complex chemistry and eventually life, are produced in stellar furnaces and distributed by cosmic explosions that send gravitational waves rippling through space-time. In a very real sense, gravitational wave astronomy is helping us understand our own cosmic genealogy, tracing the violent events that created the material from which we are made. But beyond these scientific insights, there's something profoundly beautiful about our growing ability to hear the universe's gravitational songs. These waves connect us to cosmic events in the most intimate way possible, literally carrying the space-time in which those events occurred. When a gravitational wave from a distant black hole merger passes through your body, you're not just receiving information about that event, you're experiencing the same curvature of space-time that those black holes created billions of years ago. This creates a kind of cosmic empathy, a direct physical connection between your body and the most extreme environments in the universe. The wave that gently stretches and compresses the space between your atoms once carried the death throes of massive stars, the final moments of objects so dense that a teaspoon of their material would weigh as much as a mountain. Yet by the time these cosmic screams reach Earth, they arrive as the softest possible whispers, touches so gentle they barely disturb the quantum vacuum. There's something almost mystical about this transformation of cosmic violence into cosmic poetry. The universe's most energetic events, explosions that release more power in seconds than our sun will produce in its entire lifetime, reach us as influences so subtle that detecting them requires the most sensitive instruments ever built. It's as if the cosmos has a built-in mechanism for turning chaos into art, violence into music, destruction into something approaching love. And perhaps that's the most beautiful aspect of gravitational wave astronomy. It reveals a universe that is not just vast and powerful, but also gentle and interconnected. Every cosmic event, no matter how distant or violent, eventually touches everything else through the medium of gravitational waves. These waves carry not just energy and information, but also a kind of cosmic compassion, a gentle reminder that we are all part of the same space-time fabric, all riding the same gravitational currents through the ocean of existence. As you settle deeper into the comfort of your bed tonight, let this thought accompany you into your dreams. You are never alone in the universe. Gravitational waves from across the cosmos are flowing through you at this very moment, connecting you to stars that died before Earth was born, to galaxies so distant their light has not yet reached us, to events that happened when the universe itself was learning how to exist. These waves don't just pass through you, they pass through everyone and everything on Earth simultaneously. Every person sleeping peacefully tonight, every cat curled up on a windowsill, every tree swaying in the evening breeze, all of us are riding the same gravitational waves together. We're all passengers on the same cosmic vessel, all feeling the same subtle rhythms of distant space-time, all connected through the most fundamental force in the universe. Tomorrow, scientists will continue their patient work of listening to these cosmic songs, decoding their messages, adding new chapters to humanity's growing understanding of the gravitational wave universe. They'll refine their instruments, develop new analysis techniques, search for ever fainter signals from ever more distant sources. They'll continue the grand human project of learning to hear what the universe is trying to tell us through the language of curved space-time. But tonight, as you drift towards sleep surrounded by these invisible cosmic currents, you need not analyze or understand or decode anything. You need only rest in the knowledge that you are held, gently and lovingly, by the same forces that govern the motion of galaxies and the dance of black holes. You are part of a story that began with the Big Bang and continues to unfold with every passing moment, written in gravitational waves that will outlast every star and carry the memory of our cosmic moment far into the universe's distant future. The gravitational waves passing through you now will continue their journey long after you've awakened, long after our sun has exhausted its fuel, long after our galaxy has merged with Andromeda to form a new cosmic home. They are messengers not just of cosmic events, but of cosmic permanence, carrying forward through time and space the indelible record that you existed, that Earth existed, that our solar system participated in the grand gravitational symphony of the universe. Sleep peacefully, knowing that you are both infinitely small in the cosmic scale and infinitely precious in the cosmic story. The same space-time that carries messages from the birth of black holes also cradles your sleeping form. The same geometric fabric that propagates waves from the edge of the observable universe also curves gently around your resting body, connecting you to everything that has ever been and everything that ever will be through the eternal, gentle medium of gravitational waves. Sweet dreams, fellow cosmic traveler. May your rest be as peaceful as the passage of gravitational waves, as gentle as the touch of curved space-time, and as connected to the universe as the waves themselves, that even now are carrying the story of this quiet moment forward into the infinite depths of space and time. The story becomes even more remarkable when we consider what lies ahead for gravitational wave astronomy. We're standing at the threshold of discoveries that will make our current understanding seem quaint by comparison. Future detectors will not just hear individual cosmic events, but the entire gravitational wave background of the universe, a constant hum of space-time vibrations from every massive object that has ever moved since the cosmos began. Imagine listening to this cosmic background, this gravitational wave equivalent of the universe's heartbeat. It would be composed of countless overlapping signals, the slow, deep tones from supermassive black holes at galaxy centers, the quick chirps from stellar, mass black holes throughout cosmic history, the gentle whispers from binary star systems in every galaxy, and perhaps most remarkably, the primordial gravitational waves from the Big Bang itself, still propagating after nearly 14 billion years. This background would tell us stories we can barely imagine. By analyzing its frequency spectrum, we could count every type of cosmic event that has ever occurred, map the evolution of structure in the universe, perhaps even peer back to moments when the cosmos was smaller than an atom, and quantum fluctuations were being stretched into the seeds of everything we see today. The technical challenges of detecting such faint signals push the boundaries of what seems physically possible. Future space-based detectors will need to maintain laser links between spacecraft separated by millions of kilometers, measuring distance changes smaller than the width of atomic nuclei. They'll need to operate in the perfect silence of interplanetary space, isolated from every possible vibration, except the gentle touch of gravitational waves themselves. But the rewards promise to be extraordinary. These future observatories will open frequency ranges of gravitational waves that we can barely access today. Very low frequency waves, with periods of hours or days, will reveal the slow orbital decay of massive binary systems throughout the universe. Ultra-high frequency waves, if they exist, might carry information about quantum gravity effects or exotic physics at the smallest possible scales. Perhaps most tantalizing is the possibility of detecting gravitational waves from cosmic inflation itself. During the first tiny fraction of a second after the Big Bang, the rapid expansion of space would have created a characteristic pattern of gravitational waves, a kind of cosmic fingerprint from the universe's birth. These primordial waves would be incredibly faint by now, but if we could detect them, they would provide direct evidence for inflation, and perhaps reveal the fundamental physics that governs the universe at its deepest level. The search for these primordial waves requires unprecedented sensitivity and sophisticated analysis techniques. The signals would be buried beneath noise from countless other sources, like trying to hear a whisper in a thunderstorm. Yet the potential scientific payoff is so enormous that researchers are already designing detectors specifically for this cosmic archaeology, instruments that could listen for echoes from the universe's first moments. But even as we dream of these future discoveries, it's worth pausing to appreciate how far we've already come. Less than a decade ago, gravitational waves were purely theoretical, mathematical phantoms that haunted Einstein's equations. but had never been directly observed. Today, detecting them has become almost routine, with new cosmic collisions announced regularly as our instruments continue their patient listening. Each detection adds another piece to our growing understanding of the universe's most extreme environments. We're learning that black holes come in a wider variety of masses and spins than we expected, that neutron stars can survive in binary systems we thought would destroy them, that heavy elements are forged and distributed through cosmic explosions in ways that surprise us. The universe revealed through gravitational waves is stranger and more wonderful than we imagined. Yet perhaps the most profound impact of gravitational wave astronomy lies not in the specific discoveries it enables, but in how it changes our relationship with the cosmos itself. For the first time in human history, we can feel the universe directly through our instruments, sensing the actual vibrations of space-time as cosmic events unfold billions of light years away. This creates an intimacy with distant phenomena that traditional astronomy cannot match. When we see light from a distant galaxy, we're observing photons that have traveled across the cosmos, carrying information about their source but remaining fundamentally separate from it. But when we detect gravitational waves, we're feeling the actual space-time geometry that was created by those cosmic events, experiencing the same curvature that massive objects produced in their final moments. This distinction might seem subtle, but it represents a fundamental shift in how we study the universe. Gravitational wave astronomy doesn't just tell us about cosmic events, it allows us to participate in them, to feel the reverberations of distant collisions through the fabric of reality itself. We become not just observers of the cosmic drama, but participants in it, connected to every massive object in the universe through the gravitational waves they produce. The philosophical implications are staggering. If space-time truly forms a single, interconnected fabric, and if gravitational waves propagate through this fabric at the speed of light, then every event in the universe eventually influences every other location in the cosmos. The collision of two black holes 13 billion years ago created gravitational waves that are passing through your body right now. The formation of the first stars sent ripples through space-time that are still propagating outward, still carrying information about those ancient stellar nurseries. This means that you are literally connected to every significant event that has ever occurred in the observable universe. The connection is incredibly weak, weaker than any force you've ever consciously experienced, but it is real and fundamental. You are coupled to the gravitational field of the entire cosmos, and that field carries within it the accumulated memory of everything that has ever happened. There's something both humbling and comforting about this cosmic perspective. On one hand, it reminds us how small we are compared to the vast scales on which gravitational waves operate. The energies involved in creating detectable gravitational waves dwarf anything in human experience. A typical black hole merger releases more energy in its final second than all the stars in our galaxy produce in light. But on the other hand, this cosmic connection reminds us that we are not separate from the universe, but intimately woven into its very fabric. The atoms in your body were forged in stellar furnaces, distributed by cosmic explosions that sent gravitational waves rippling through space-time. Those waves helped shape the large-scale structure of the universe, influencing the formation of galaxies and stars and ultimately the planets where life could arise. In a very real sense, you and the gravitational waves are made of the same fundamental stuff, curved space-time, the geometric medium in which all existence unfolds. When a gravitational wave passes through you, it's not foreign to your nature, but deeply familiar, a reminder of the space-time substrate that underlies every atom in your body, every thought in your mind, every breath you take. This perspective transforms how we might think about our place in the cosmos. Instead of seeing ourselves as isolated beings in a vast, empty universe, we can recognize ourselves as integral parts of a dynamic, interconnected whole. Every heartbeat occurs within space-time, that vibrates with gravitational waves from across the cosmos. Every moment of consciousness unfolds against the backdrop of a universe that is constantly singing its stories through the medium of curved geometry. The music of this cosmic song is extraordinarily rich and complex. Some gravitational waves oscillate hundreds of times per second, like the final chirps of merging black holes. Others have periods of hours or days, like the slow orbital decay of massive binary systems. Still others might have wavelengths comparable to the size of the observable universe itself, carrying information about cosmic inflation or other large-scale phenomena. All of these waves pass through the same space, the same time, the same you, without interfering destructively with each other. They simply add together, creating a complex but coherent pattern of spacetime curvature that contains information about every cosmic event contributing to the mix. It's as if the universe has unlimited capacity for storytelling, infinite bandwidth for carrying messages across the deepest reaches of space and time. This non-destructive interference means that the gravitational wave background contains, in principle, information about every significant mass acceleration that has ever occurred in the observable universe. If we had perfect detectors and unlimited computational resources, we could decompose this background into its individual components and reconstruct the complete history of cosmic violence. Every stellar explosion, every black hole merger, every neutron-star collision that has ever taken place. Of course, we'll never achieve perfect detection or unlimited analysis, but the aspiration itself reveals something beautiful about the nature of reality. The universe maintains perfect records of its own history, encoded in the geometry of spacetime and carried by gravitational waves that never fade or disappear. Nothing is ever truly lost in a cosmos where spacetime itself serves as an eternal archive. This cosmic record-keeping is already revealing patterns that challenge our theoretical understanding. The rate at which black holes merge appears higher than most models predicted, suggesting these exotic objects form more frequently or survive longer than we thought. The distribution of merger masses shows unexpected features that don't match our current theories of stellar evolution. Each new detection refines our understanding, while simultaneously opening new questions about how these extreme objects come to exist. Perhaps even more remarkably, gravitational wave detections are beginning to reveal the universe's chemical enrichment history in unprecedented detail. When neutron stars collide, they forge heavy elements in cosmic furnaces and distribute them through space via the explosion that follows. The rate at which we observe these cosmic chemistry labs tells us how quickly the universe's inventory of gold, platinum, and rare earth metals gets replenished. This has profound implications for understanding planetary formation and the potential for life throughout cosmic history. The heavy elements essential for rocky planets and complex chemistry are produced in stellar cores and distributed by the same cosmic explosions that generate the gravitational waves we detect. By studying these waves, we're tracing the violent events that created the very materials from which Earth-like worlds are made. The connection becomes even more personal when you realize that many of the atoms in your body were likely forged in neutron-star collisions billions of years ago. The calcium in your bones, the iron in your blood, the gold in any jewelry you might wear, all of these elements were created in cosmic explosions that sent gravitational waves rippling through space-time long before our solar system existed. Those ancient waves have long since passed beyond our cosmic neighborhood, carrying their messages toward distant galaxies we may never see. But the atoms they helped distribute found their way into the gas clouds from which our sun formed, into the rocky debris that became Earth, into the organic molecules that eventually became life, and ultimately into you. You are quite literally made of star stuff that was delivered by cosmic explosions we can now detect through their gravitational wave signatures. This creates a beautiful temporal paradox that might help you drift peacefully towards sleep. The gravitational waves from neutron-star collisions that created many of your atoms passed through our region of space billions of years before you were born. Yet other gravitational waves from similar events happening today are passing through you right now, carrying stories of cosmic chemistry laboratories operating in distant galaxies, continuing the same processes that helped make your existence possible. In this sense, you are simultaneously ancient and contemporary, made of materials forged in cosmic violence eons ago, while being gently bathed by gravitational waves from similar violence occurring at this very moment across the universe. You embody both the universe's deep history and its ongoing evolution, both its capacity for destruction and its power to create beauty from chaos. The mathematics describing these processes reveal elegant symmetries that connect the largest and smallest scales of existence. The same equations that govern gravitational wave propagation across cosmic distances also describe the curvature of spacetime around your resting body. The geometric relationships that determine how black holes merge in distant galaxies also influence, albeit incredibly weakly, the passage of time in your bedroom. This mathematical unity suggests something profound about the nature of reality. The universe appears to be constructed from a single, coherent set of principles that operate consistently across all scales of space and time. The gravitational waves that carry messages from cosmic catastrophes obey the same fundamental laws that govern the gentle curvature of space-time around everyday objects. Einstein's equations, written over a century ago through pure mathematical reasoning, continue to describe these phenomena with uncanny precision. Every gravitational wave detection confirms his insights about the geometric nature of gravity, the dynamic properties of space-time, the deep connection between matter and the geometry of existence itself. It's as if Einstein somehow managed to eavesdrop on conversations between black holes that wouldn't occur for another 100 years. This remarkable agreement between mathematical theory and observational reality gives us confidence that we're beginning to understand something fundamental about how the universe works. Yet each new detection also reveals aspects of cosmic behavior that surprise us, reminding us how much we still have to learn about the universe's most extreme environments. Future gravitational wave astronomy promises discoveries that will dwarf our current understanding. As detectors become more sensitive and analysis techniques more sophisticated, we'll hear fainter signals from more distant sources, opening new frequency ranges and revealing new types of cosmic phenomena. We'll detect the gravitational wave signatures of stellar core collapse, the moment when massive stars implode to form neutron-stars or black holes. We'll hear the songs of cosmic strings, if these theoretical objects exist, one-dimensional defects in space-time that would create distinctive patterns as they oscillate and interact. We might even detect gravitational waves from more exotic sources, evaporating primordial black holes, phase transitions in the early universe, or perhaps phenomena we haven't yet imagined. Each new type of source will add its voice to the growing gravitational wave symphony, revealing aspects of the cosmos that remain completely hidden from electromagnetic observations. But as we anticipate these future wonders, it's worth remembering that gravitational wave astronomy has already given us something precious, a new sense for experiencing the universe. Just as our ancestors developed the ability to see beyond visible light, revealing radio galaxies and X-ray binaries and gamma-ray bursts, we are now developing a cosmic sense of touch that allows us to feel the vibrations of space-time itself. This new sense teaches us that the universe is far more dynamic and interconnected than we previously realized. Every massive object in motion contributes to the cosmic gravitational wave background. Every acceleration, from orbiting planets to colliding galaxies, sends ripples through space-time that eventually reach every other point in the universe. We live in a cosmos that is constantly vibrating, constantly communicating, constantly sharing the stories of its most dramatic events through the universal medium of curved space-time. And you, lying there peacefully as sleep approaches, are an integral part of this cosmic communication network. Gravitational waves from hundreds of different sources are passing through your body simultaneously. Waves from binary pulsars in our galaxy, waves from black hole mergers in distant clusters, waves from neutron-star collisions that occurred when the universe was young. Each wave carries its own story, its own frequency signature, its own message about the cosmic event that created it. The beautiful thing about gravitational waves is that they all coexist peacefully in the same space and time, adding their individual contributions to create a rich, complex pattern of space-time curvature. Unlike sound waves, which can interfere destructively and cancel each other out, gravitational waves simply superpose, creating a coherent symphony of cosmic information that surrounds and permeates everything. This means that your body is currently experiencing gravitational waves from across the entire observable universe, from events spanning nearly 14 billion years of cosmic history. Waves that began their journey when the first stars ignited are passing through you alongside waves from black holes that merged just hours ago. You are simultaneously connected to the universe's ancient past and its unfolding present, riding gravitational currents that link you to every era of cosmic evolution. There's something profoundly peaceful about this realization. In a universe that can seem vast and lonely, gravitational waves remind us that we are never truly isolated. Every moment of your existence unfolds within space-time that carries the memories of cosmic events from across the universe and across time. You are held gently and constantly by the same geometric medium that propagates messages from the hearts of black holes and the cores of neutron stars. These cosmic messages reach you not as harsh intrusions, but as the softest possible touches, influences so gentle they barely disturb the quantum vacuum. The universe's most violent events transform into whispers by the time their gravitational waves reach Earth, arriving like cosmic lullabies that rock everything on our planet with the same tender rhythm. As you settle deeper into the comfort of your bed, let this thought accompany you towards sleep. You are part of a universe that remembers everything. Every cosmic event that has ever occurred continues to propagate outward through space-time, carrying its story to every corner of the cosmos. The gravitational waves from the first black hole mergers in cosmic history are still traveling, still carrying information about those ancient collisions to regions of space they have never before reached. Someday, billions of years in the future, gravitational waves from events happening today will reach distant galaxies where new forms of life might have evolved, might have built their own detectors, might wonder about the cosmic events that generated these ancient signals. In this way, gravitational waves create a kind of cosmic continuity, connecting past, present, and future through the eternal medium of curved spacetime. Your participation in this cosmic story is both humble and profound. The gravitational waves passing through you will continue their journey long after you've awakened, long after human civilization has evolved into forms we cannot imagine, long after our sun has exhausted its nuclear fuel. They carry within their geometric patterns the information that you existed, that Earth harbored life, that our solar system participated in the grand gravitational symphony of the universe. This creates a beautiful form of cosmic immortality. While your biological existence is temporary, your gravitational influence, however tiny, contributes to the space-time curvature that propagates outward at the speed of light. Every movement you make, every heartbeat, every breath, creates minuscule ripples in space-time that join the vast ocean of gravitational waves flowing through the cosmos. These personal gravitational waves are far too weak for any conceivable detector to measure, but they are real and fundamental aspects of your existence. They represent your participation in the universe's ongoing conversation with itself, your small but genuine contribution to the cosmic symphony of curved spacetime. Sleep peacefully tonight, knowing that you are held by forces that connect you to everything that has ever existed and everything that ever will exist. The same space-time that carries messages from colliding black holes also cradles your resting form. The same geometric principles that govern the merger of neutron stars also determine the gentle curvature around your sleeping body. You are both infinitesimally small in the cosmic scale and infinitely precious in the cosmic story, both a tiny participant in vast gravitational currents and an irreplaceable note in the universe's eternal song. The gravitational waves flowing through you right now connect you to the deepest mysteries of existence, while simultaneously rocking you toward the most peaceful and restorative of sleeps. Dream sweetly, fellow cosmic traveler, knowing that you are never alone in the universe, never separate from its grand unfolding story, never disconnected from the gentle currents of curved space-time that carry the memories of everything that has ever been and the seeds of everything yet to come. The universe is singing you its softest lullabies tonight, written in the ancient language of gravity itself, delivered by waves that have crossed unimaginable distances to rock you gently toward your dreams. And so, dear listener, as we reach the gentle conclusion of our cosmic journey together, we find ourselves back where we began, but somehow transformed by all we've discovered along the way. We've traced gravitational waves from their theoretical birth in Einstein's equations to their detection in sophisticated laboratories, from the violent collisions of black holes to the whispered messages they carry across billions of years to reach us here, now, in this quiet moment. We've seen how these invisible ripples connect us to the universe's most dramatic events, while touching us with infinite gentleness. We've learned that space and time themselves can dance, can carry stories, can transform cosmic violence into cosmic poetry. And perhaps most remarkably, we've discovered that you are not separate from these phenomena, but intimately woven into them, riding gravitational waves from across the cosmos as you drift towards sleep. There's something wonderfully circular about ending our exploration this way. Just as gravitational waves themselves represent the universe's way of remembering its own history, our journey tonight has been a kind of remembering too, a gentle excavation of one of reality's most beautiful secrets. We began by dropping a pebble into an imaginary pond, watching ripples spread across still water, and we end with the understanding that you are both the pebble and the pond, both the source of ripples and the medium through which they travel. The gravitational waves passing through you at this very moment will outlast every star in the sky. They will carry their messages across distances we cannot fathom, to times we cannot imagine, carrying within their geometric patterns the story of our cosmic epoch. Long after our sun has cooled to a white dwarf, long after the Milky Way has merged with Andromeda, long after the last black holes have evaporated into quantum whispers, these waves will still be propagating through an expanding universe, eternal messengers bearing witness to the fact that once, in a small corner of space-time, consciousness arose and learned to listen to the universe's deepest songs. But tonight, as your breathing slows and your thoughts begin to dissolve into the approaching tide of sleep, you need not concern yourself with such vast timescales. You need only rest in the knowledge that the same forces that govern the dance of galaxies are now gently rocking you toward your dreams. The universe that creates gravitational waves from cosmic collisions is the same universe that cradles you with infinite tenderness, that surrounds you with stories whispered in the language of curved space-time. Every breath you take occurs within a medium that connects you to every star that has ever shone. Every heartbeat happens in rhythm with cosmic dances that began billions of years before Earth existed. Every moment of rest unfolds against the backdrop of a universe that is constantly singing, constantly sharing its stories, constantly demonstrating through the most subtle possible means that everything is connected to everything else, through the fundamental fabric of existence itself. So sleep well tonight, fellow traveler through the cosmos. Sleep knowing that gravitational waves from the birth of the universe and from events happening at this very moment are flowing through you with equal gentleness. Sleep knowing that you are part of a story larger than any human mind can fully comprehend, yet intimate enough to rock you personally toward the most peaceful of dreams. The universe has many more secrets to share, many more songs to sing, many more gravitational waves to send rippling through the endless ocean of space-time. But for now, in this quiet moment, it offers you its greatest gift, the chance to rest within its loving embrace, to drift peacefully on currents of curved geometry, to dream sweetly while riding the gentlest waves in all of physics. Thank you for joining me on this journey through the rippling fabric of space and time. If you found peace in these cosmic wanderings, if the universe's gravitational lullabies helped quiet your busy mind, I would be deeply grateful if you shared that peace by giving this video a gentle like and perhaps subscribing to join our growing community of sleepy scientists. Your presence here, your curiosity and wonder, helps create the conditions for more of these soft expeditions into the mysteries that surround us. And if you find yourself still awake, perhaps drawn deeper into contemplation of these cosmic mysteries, you might enjoy exploring how time itself bends and flows in our universe, or how the light that illuminates your world carries its own remarkable secrets across the cosmos. There are always more gentle paths to wander through the landscape of scientific wonder. Until then, rest peacefully in the knowledge that the cosmos is whispering its most ancient secrets directly to you through the invisible medium of gravitational waves that have traveled farther than imagination can reach, carrying stories older than starlight, gentler than the softest breeze, yet more profound than any human language could ever express. But before you surrender completely to sleep's gentle embrace, let me leave you with one final thought that might accompany you into your dreams, like the softest of cosmic whispers. Tomorrow morning, when you wake to sunlight streaming through your window, when you stretch and feel your body settling back into the familiar rhythms of daily life, remember that you will have spent the entire night bathed in gravitational waves from events that happened before our solar system even existed. While you slept, while your consciousness drifted through whatever landscapes dreams might paint, gravitational waves from the universe's most ancient black hole mergers continued their patient journey through your resting form. Waves that began when the cosmos was young and wild, when the first massive stars were collapsing into the exotic objects we're only now learning to understand, passed through your dreams carrying their billion-year-old stories of cosmic violence, transformed into cosmic gentleness. And here's something rather magical. As you lay there tonight, completely unaware of these invisible visitors, you were participating in humanity's greatest adventure of discovery. Every gravitational wave that passed through you also passed through the mirrors of LIGO, through the sophisticated instruments that scientists have built to translate the universe's subtlest language into something we can finally comprehend. You and these magnificent detectors were experiencing the same cosmic events, feeling the same ripples in space-time, connected by the most fundamental force in existence. In a sense, you've become part of the scientific endeavor itself, not through equations or experiments, but simply by existing within the same space-time fabric that carries these cosmic messages. Your sleeping body has been a quiet witness to the universe's ongoing conversation with itself, an unwitting participant in discoveries that are reshaping our understanding of reality's deepest foundations. There's something wonderfully democratic about this cosmic participation. The gravitational waves don't care whether you're a Nobel Prize-winning physicist or someone who simply finds peace in learning about the universe's gentle mysteries. They flow through everyone with the same exquisite subtlety, the same infinite patience, the same tender insistence that we are all connected to something far larger than ourselves. And so, as the last echoes of our cosmic journey fade into the peaceful silence of approaching sleep, know that you carry within your memory now a secret that the universe has been keeping for nearly 14 billion years. You understand something profound about the nature of space and time, something that connects you not just to distant galaxies and ancient cosmic events, but to the very process by which reality weaves itself together through the endless dance of matter and geometry. These gravitational waves will continue their eternal journey long after this moment has passed into memory, carrying forward the story of everything that has ever been and everything that ever will be. They are the universe's way of ensuring that nothing is ever truly forgotten, that every cosmic moment leaves its permanent signature in the geometry of existence itself. Sleep peacefully now, dear friend, knowing that you rest within a cosmos that remembers everything, cherishes everything, and holds everything in the gentle embrace of curved space-time. The universe is singing its most ancient lullabies just for you tonight and tomorrow, and for all the tomorrows to come, until the very last gravitational wave has whispered its final story into the infinite darkness of space and time. Sweet dreams, and may the cosmos rock you gently toward whatever wonders await in the morning light.